In this video, we are going to go over the first two pages of section 4.5 notes, and 4.5 notes looks at rational functions. So when you hear the word rational in math, I want you to think fraction. So we're going to look at functions that are basically a fraction. Now, keep in mind when we work with a fraction, one thing that we can never ever divide by is 0. And so when we look at these graphs, we have to keep that in mind. That means that wherever there's an x value that would make our denominator equal 0, we're going to have a discontinuity. Okay, so looking at our function f of x, notice that it is in that mixed number form. That should sound familiar from previous sections, as this is the form you would get after you would do long division or synthetic division. This form helps us see a lot of things about the graph that we'll talk about later. But ultimately, looking at the fraction part of this function, notice I factored it, the numerator and denominator over here, and that helps us see in the denominator what x cannot equal. So looking at this, I see that x cannot equal -4 and x cannot equal -3, because if they did, if we plug them in, we'd divide by 0, which again is not allowed. So at -4 and -3, we're going to see disruptions or discontinuities in our graph. And so what a discontinuity means is if you were to try and draw this graph, draw this function, this piece here, you would have to pick up to jump over this asymptote, and then you would pick back up here, but you'd have to pick up your pencil again to jump over that hole. And so a discontinuity would mean you have to pick up your pencil or your writing utensil to keep drawing this function. So clearly we have two discontinuities. We have a hole and we have an asymptote. The vertical asymptote comes from right here. X cannot equal -4. Now the other discontinuity that we see is at -3 and is the hole. So the reason why we have a hole here instead of an asymptote is because that factor is on both the numerator and the denominator. So technically we could cancel it and it'd turn into a 1. However, this function started with it, so our graph has that discontinuity there. And so a removable discontinuity is found by what can be canceled. So in this case, at x equals -3. A vertical asymptote is what remains in the denominator after canceling. So in this case, x equals -4. So before you ever start graphing a rational function, it's really nice to first identify your discontinuities. Where am I going to have disruptions in the graph? So right away, that vertical asymptote at -4 tells me I'm never going to cross there, so I'm going to have a piece to the left and a piece to the right. This hole tells me I'm going to have to hop over that at some point. So the next piece of the graph that we want to look at are non-vertical asymptotes. So non-vertical, we could see then horizontal or a slant. So we have three different cases that we're going to look at. And so this first one here, looking at the leading terms in the top and the bottom, I can see that I have an x squared is my highest power in the denominator and x is the highest power in the numerator. So in this case, our degree is higher in the denominator. And we'll talk about why that's significant here in a second. Notice with my second example, the degree is higher in the numerator. And then our last example, the degrees are the same. Okay, so when we talk about vertical asymptotes, we're talking about what we can or cannot plug into our function. When we talk about non-vertical asymptotes, we want to know what types of numbers would be spit out of this function long term. And so what we think about is if we were to plug really, really large numbers in for x, as x goes off to infinity, what happens to my outputs? What's the behavior of this graph doing? So if I were to plug in, let's say, a really large number into the numerator, let's say 1,000,000, I'd have 3,000,000 plus 9, so 3,000,009. When you're talking about really, really, really large numbers, we don't even really care about that 9 anymore. When you're talking about 3,000,000, who cares about 9 ones? So we can kind of ignore the 9, we can ignore the 12, and we could also ignore this 7x, because look right here, we're about to square 1,000,000. So if we were to plug in 1,000,000 in for x, we'd have 3,000,000 and over 1,000,000 squared. So we can kind of ignore these because they'd end up being super small as we head off to infinity. And so if we had 3,000,000 over 1,000,000 squared, my denominator is going to be way bigger than my numerator. If I plug in 2,000,000, a billion, no matter what I plug in, my denominator is always going to be way bigger than my numerator because this is an x squared. And we know if we divide by big, big numbers, overall, as a whole, this whole fraction will be small. So what we say is x gets super, super big as x approaches infinity, gets large. Our function, or our output, will get smaller and smaller and smaller and pretty much equals 0. And so over here, we have a horizontal asymptote at y equals 0. And that's what happens when our degree is higher in the denominator. So if our denominator gets way bigger, overall the fraction gets smaller and approaches 0. Okay, in the next one, our degree is higher in the numerator. Same idea but reversed. If we were to plug in really, really large numbers like a billion cubed times 3 over a billion squared times 2, no matter what, who cares that we're multiplying by 3 and 2, who cares about this x and this 2 and this 5x, if I were to take a billion cubed over a billion squared, the numerator is going to be way bigger always. And so we would say as x gets bigger or approaches infinity, our function will get bigger as well and also approach infinity. And so if you kind of look at this behavior, it kind of follows this pattern here. It kind of looks like it'd follow a line, and so we call that a slant asymptote. And remember, this one was a horizontal asymptote. Okay, so again, if your function is approaching infinity, you would expect to see a slant asymptote. So for the last one, the degrees were the exact same. So let's say you put in 1,000,000. You have 1,000,000 squared times 3 over 1,000,000 squared times 6. Let's say you put in a billion squared times 3 over a billion squared times 6. Again, I'm ignoring this because these little terms here really don't hold much significance when you're squaring a billion. These numbers are way bigger, so we can kind of ignore those. So if you have 3 times a billion squared over 6 times a billion squared, notice that these billion squares would kind of cancel, and you're left with 3 over 6, which is 1/2. So as x gets bigger and bigger and bigger, I'm always going to have half the amount in the numerator as I do in the denominator. And so it'll kind of level off around 1/2. Our function will get closer and closer and closer to 0.5 because again, our numerator is going to be roughly half of our denominator. And so as you get super far out there, your outputs will be roughly 0.5. And so this would be another horizontal asymptote. Oops, and this horizontal asymptote would be at y equals 0.5. Okay, so we'll come back to this idea a little later. Improper fractions. So improper fractions can be written in mixed number form. We kind of talked about this. So it's important to get your function in mixed number form in order to see different key features of the graph. And so once you write them in mixed number form, again, you do that by dividing the polynomials. We did that last couple sections using synthetic or long division. The reason why mixed number form is helpful is what it tells us about the graph. So anything that looks like this would be considered mixed number form, where this was your remainder. So you divide, you got your remainder. This piece right here we called the divisor, or whatever was in the denominator. And then this piece is the part that looks like a polynomial. No fraction. So what's nice about this is this polynomial part will give you the non-vertical asymptotes. So that's what we just talked about, or all the different reasons why we have non-vertical asymptotes. This one was y equals 0.5. This one was a slant. It followed some sort of slant here. This one was 0. Once you get it into mixed number form, whatever was the polynomial part will be that non-vertical asymptote. And again, we'll look at a lot more examples later on in your notes. Okay, so moving to the next page. So here's an example, and we want to find our non-vertical asymptotes. So before you do that, it's always a good rule of thumb to factor your function, see if anything cancels. Otherwise, we're going to have to use long division since we're dividing by a quadratic. I like to use synthetic, so if we can get some things to cancel, we might be able to use synthetic division instead. So the top will factor into x minus 1, x plus 5, where the denominator will factor into an x minus 7, x minus 1. And like I said, since something cancels right here, x minus 1 and x minus 1, we can actually use synthetic division. Let's make a note, we'll talk about this later, but that would mean that we would expect to see a whole at x equals 1. That would be a removable discontinuity since they canceled top and bottom. So what we are left with is x plus 5 over x minus 7. Real quick, just kind of thinking through the graph of this, we know that we would have a whole at x equals 1, and we know that we'd have a vertical asymptote at 7. Also, looking at this degree right here, notice the degree is the same, so you could look at the coefficients, which would be 1. So I'd expect a horizontal asymptote at 1. Again, we said a whole at x equals 1. So we would expect our graph to look something like that, and maybe the other piece would be over here. Okay, that's looking ahead. We'll talk a lot more about why the graph would look that way. For now, we're finding non-vertical asymptotes, which again, I kind of guessed that that would be at 1. But we're going to see for sure, and we're going to see for sure by dividing this and putting it into mixed number form. Again, I can do that by synthetic division. Oops, sorry, I lost my spot. There we go. So I'm going to plug in 7 since I'm dividing by x minus 7. My coefficients of x plus 5 are 1 and 5. Leave a space, draw a line, bring down your 1, multiply by 7, add to the 5, we get 12. Remember that first number is always your remainder. We put it over our divisor. This would be all that's left for our polynomial part. And so there is our function f of x in mixed number form. So again, having it in mixed number form is nice because this polynomial part tells us our non-vertical asymptotes. So what we just found is we would have a non-vertical asymptote at y equals 1, which, looking at this super rough sketch that I made over here, we know that our non-vertical asymptote would be at 1. Again, looking at the degrees, they were the same in the top and bottom. So you then can just look at these coefficients, which are 1 over 1, which verifies non-vertical asymptote is at 1. Okay, so here's a couple more examples of those, that same idea. I have each of these functions in improper form and in mixed number form. Again, that polynomial piece will help us find the non-vertical asymptotes. So right here, the polynomial part was 2. Our horizontal asymptote would be at 2. After you divide these, we get 4. Horizontal asymptote's at 4. Improper form, mixed number form, polynomial part's at 1. Our horizontal asymptote would be at 1. Remember, asymptotes we write as equations of lines, y equals 1, y equals 4, y equals 2. Now, again, the shortcut way, so you don't have to divide them every single time, is our exponents are the same in the top and bottom, x squared over x squared, x over x, x squared over x squared. When that's the case, you're able to just look at the coefficients. 2 divided by 1 is 2. 4 divided by 1 is 4. 1 divided by 1 is 1. Okay, so with our non-vertical asymptotes, we just covered horizontal asymptotes. And so next we will look at slant asymptotes. So again, we want to first factor our function to see if anything cancels. So the top will factor into x plus 4, x minus 4 over x minus 5. Nothing cancels. That means that we're going to just have to divide as is. In that case, since we are dividing by an x minus 5, we have no problem using synthetic division. Plugging in 5, our coefficient of x squared is 1. We don't have an x term, so make sure you fill that in with a 0. And then my last term is negative 16. Leave a space, draw a line, bring down your 1, multiply by 5. We get 5, add it to the 0, 5 multiplied by 5, 25, add it to the negative 16, we get 9. So now we can rewrite our function f of x. Remember, 9 is the remainder. We put it over our divisor, x minus 5. 5 is our coefficient, or our constant, where 1 is the coefficient of our x term. So, remember, the reason for writing it in mixed number form is that the polynomial part is our non-vertical asymptote. So that means that we have a slant asymptote at x plus 5. So, looking at this graph compared to its function, x minus 5, we know x can never equal 5. That's where we get this vertical asymptote from. We don't have any holes because no factors canceled. Then, looking at our function in mixed number form, this polynomial part, x plus 5, gave us this slant asymptote. And so our function gets super, super close to this asymptote and super, super close to that asymptote. It has two pieces to it. and looks like that. Okay, so asymptotes are going to help us kind of figure out end behavior or what's happening to our graph. But to get more precise, we want to know what the x and y intercepts are. So remember, x-intercepts are found on where y would equal 0. When can we get out a 0? Now we know our denominator is never going to equal 0. So for rational functions like this, we find our x-intercepts by figuring out where the numerator is equal to 0. Now our y-intercepts are a lot easier because they happen when x equals 0. So you just plug in 0 where you can, and that would give us our y-intercept. So x-intercepts, again, we want this whole thing to eventually equal 0. I'll go ahead and bring it down here. We know our denominator is never going to be equal to 0, so we look at our numerator to help us find our x-intercepts. Note that they would happen at x equals 4 and -4. And so comparing that to what we see on the graph, here was +4 and there was -4. Our y-intercepts happen when x equals 0, so we can just plug in 0 wherever we see an x. We will end up with 4 times -4 up top over -5. So we'll end up getting a +16/5, which is roughly 3.2. So looking at our y-axis, it definitely looks like it crosses at about 3.2. Okay, that is it for notes today. The next video for tomorrow will continue on how to find these key features of these rational functions. Just to kind of close, remember, rational means fraction. We find our discontinuities, our asymptotes, or our holes by looking where the denominator would equal 0. To figure out what's happening long term, those are called our non-vertical asymptotes. They could either be horizontal or they could be slant. Here are the 3 different cases that we could see depending on where the degree is higher, but ultimately that mixed number form helps us when we can see that polynomial part.